And we come to the next speaker.
Thank you, Tunga. I'm very pleased to introduce Professor Richard Corsi, who is the ECH Bantel Professor for Professional Practice and Chair of the Department of Civil, Architectural, and Environmental Engineering and co-director of the Center for Sustainable Development in the School of Architecture at the University of Texas in Austin. Professor Corsi has had over 70 research projects covering areas of sources, physics, chemistry, exposure, and controls of indoor air pollution. He has been featured in National Geographic, The Economist, Business Week, National Public Radio's Science Friday, The Nature of Things, and quite a few other popular outlets for science. He was named a distinguished alumnus of the Humboldt State University in 2006 and is a member of the ISIAC Academy of Fellows. He's also was president of Indoor Air 2011, which many of you recall, and is an associate editor of Indoor Air. I'd like to note that on a more personal note, I think he is one of the best mentors in our field. He is quite beloved by his students, and as a result has received many teaching awards. He's also a well-known vegetarian and animal lover, and a very dear friend.
Good stop now. So, thank you, Glenn, and thank all of you for still being here. It's always great to see. This is a pretty big crowd for a last afternoon of a week-long meeting, and especially thank Hugo Lee and his steering committee and his organizing committee for an absolutely wonderful conference. It's been a great week, so round of applause. My presentation is entitled Challenges and Opportunities for the Indoor Air Sciences Community. Implicit in the title is that I'm going to speak about the future. And if we speak about the future, we need to speak about youngsters, the young scientists, the students, postdocs, young faculty amongst us. And so my presentation today is really focused on you, those that are young in the audience. So all the old farts can leave if you'd like to, but I'm going to focus on young people. And I'm also going to focus on connections, because I think that in the future, we're not going to be able to overcome grand challenges that face us as a community without making connections between the subdisciplines in our field, microbiologists working with engineers, chemists working with public health folks, and so on and so forth. And I don't think we're going to realize the opportunities as a field unless we make connections. So really the theme of my presentation for the young people that are here today is connections. The importance of buildings and indoor air quality. The first line up here is a series of numbers, a series of 5 numbers. These numbers vary a little bit from country to country, so I'm showing you the numbers for my country, the United States. And what these numbers correspond to, the first number is the average life expectancy in years of an American. 78.7 years is our current life expectancy. The second number is the number of those 78.7 years that we will spend inside of buildings during our lifetime. 70 of our 78.7 years. We spend a greater percentage of our time inside of buildings than all the whales of the world spend submerged below the surface of the ocean. So one might say, are buildings our ocean? We spend so much time in buildings, and that's one of the reasons we should be interested in buildings. The third number is the number of years in a lifetime that we spend inside of our own home. 50 years. So if we're worried about exposure to stuff, whatever that stuff is, we ought to look right in our own homes. That which is supposed to shelter us might be the place where we get our greatest exposure to stressors. The fourth number is the number of years that we spend lying on a mattress, sleeping. There's no other microenvironment in our lives where we spend more time than lying on a mattress. Yet if you look in the literature, there's very little study on what people are exposed to when they're sleeping and how that affects them. Right? There were some great papers at this conference, in fact, a workshop on that subject, and I hope that this conference sort of stimulates more research in that area. The last number is the number of years in our lifetime we as Americans spend outdoors. Now, in developed countries, those numbers will change slightly, but they're not going to change that much. We spend most of our lives inside of buildings. Buildings have a direct impact on our lives, on health, comfort, and productivity. It's interesting if you try to find a number for the number of buildings there are in the world, you can't find a good estimate. You see estimates that are all over the place, anywhere from 1 to 3 billion buildings in the world. So we haven't cataloged buildings very well, but there are a lot of buildings, and every single building is different from every other building, which adds to a lot of complexity in our field. We're dealing with billions of different fingerprints in terms of buildings. Buildings are a substantial asset to humans. Just an example, in my country, residential buildings alone, forget about commercial and institutional, residential buildings in the United States are valued at greater than $20 trillion. That's more than 10% of the total assets of the United States, and that includes military hardware, farm machinery, everything. So buildings are valuable, and we need to worry about taking care of them. And then buildings impact the natural environment. You know, this conference is focused on what happens in the indoor environment, but things we do for buildings impact the natural environment. And I'll give you an example, and that's, or maybe not. Here we go. Flame retardants. We know that flame retardants and other persistent organic pollutants will accumulate in human fat, accumulate in breast milk, accumulate in seminal fluids, but those same compounds also accumulate in the fat of sperm whales, orcas, polar bears, penguins, and there's even some research coming out now that's showing that honey produced around the world has increasing levels of flame retardants in it, and nobody's actually been able to figure out why. So, interesting, we can see here polar bear bones are weakened by certain pollutants, including brominated flame retardants. What's important here is that use in buildings of these persistent organic pollutants like flame retardants drive much of the production of these things. It's for buildings that they're being produced, and by producing these things to put in buildings, particularly at manufacturing sites, they're released into the environment and affect the natural environment. So buildings affect the natural environment just like they affect the interior environment. There we go. Okay. So research on buildings. I think research on buildings and indoor air quality is quite exciting. They're complex systems. We're dealing with heterogeneous systems. Buildings are not homogeneous. They're not monoliths, homogeneous monoliths. They're dynamic. They change on scales of seconds to decades. Indoor air quality research is dynamic. I went back to Indoor Air 1999 proceedings a few days ago, and I looked through the proceedings. The number of papers on semi-vol organic compounds in Edinburgh in 1999 was 2. 2 papers, neither one of them dealt with health effects. It was just, we found this stuff in dust. So in just 15 years, there's almost been an industry around flame retardants and phthalates that have been generated in our field that didn't exist 15 years ago. If you do a search on climate change for Indoor Air 1999, there's nothing. Nobody was talking about climate change effects on indoor air quality 15 years ago in Edinburgh. So it's a dynamic field, it's a complex field. We still are grappling with what causes sick building syndrome. We still don't know the causative agents of health effects in damp buildings. There's still a lot of work to be done on things that we've been working on for a long time. So our field is of great intellectual merit. I think it's ripe for cross-disciplinary research and innovation. That's where we'll make the connections to deal with challenges of the future. And it's still a wide open research frontier. There's so much work to be done for the young people that are here. So I just want to talk about 3 or 4 challenges. There are many challenges that face us, and I just came up with 3 or 4 examples. But a couple of words about how I see challenges. I see challenges as being challenges of external obstacles or complexities. That means things that are beyond our control. A challenge for us is getting research money from our government agencies. That's an external challenge. So that's one challenge that we all face. Another is the challenge of oneself. That's an internal obstacle that we can overcome. And I want to implore one more time that we need to make connections with people that do things that are different than us. You know, engineers have to be willing to work with health scientists and vice versa. And that's a way of overcoming those challenges. And challenges often birth opportunities. In fact, I think the greatest accomplishments of humankind have come when we've been challenged. You know, eradicating polio. We're challenged by a horrible disease, and we have to overcome. How do we get over this? Going to the moon, going to space, great challenge, right? And it generates an opportunity for us. We have to think about what our grand challenges are. I think that Jenny just spoke about one of our grand challenges, and that's how to deal with a future that has all sorts of changes in it related to climate change. Jan Sundell in the first plenary talked about the importance of linking everything we do to health, and I think that is a big challenge for us. It's why we do what we do. We want to make better buildings. We want to make buildings where people are healthier, more productive, better environments, essentially, learn better. And unless we can link what we do to health, we're not going to have a fuel to grow our field. People that give money are going to respond if we find links to health and productivity and learning, and we need to do that. We need to avoid the lure of the silver bullet. You know, we are breathing right now. We're swimming in an ocean of a mixture of biological agents and chemical agents, and sometimes we sort of narrowly focused on one thing, and we get all excited if we see a high level of one thing. But we're really exposed to a lot of things at once, and one of the things that I didn't hear much of at this conference was the effect of cumulative exposures. All right? In 2011, one of our plenary speakers, Tracy Woodruff, actually showed these results right here, showing exposures to 2 different phthalates and how you get certain health effects. These are reproductive effects in the male offspring of rats if you're exposed to DEHP or DBP, but in combination you have essentially dose additive effects and much greater effects when you're exposed to these 2 things together. And also you can even take something like a phthalate and linneron, which have disparate mechanisms of toxicity. This is basically an herbicide and a phthalate, and you get tremendous health effects, reproductive effects, if you combine those 2 chemicals. So we need to start thinking more about cumulative exposures and effects. And, you know, epidemiology is very, very important for us to make health links. How many people in the audience have degrees in toxicology? 1. I think I saw 1. And I think that's something that we need to embrace more as a community and work with toxicologists, bring them into our community and be willing to work with them. I did a Twitter poll about 3 weeks ago. I tweeted out and asked people to give me what they thought were the biggest challenges they had in their research or their practice related to indoor air quality. The #1 response that came back was dealing with the avalanche of green stuff that's coming onto the market that they have no information about. Applications of green products, green materials, green protocols are far outpacing the ability of science to keep up with what the impacts of all those things are, for better or for worse. Right? How do we keep up? How do we prioritize? What are the impacts of different green products and materials on health, on productivity and economics, chemistry, material integrity, microbiology? Are green walls good or are green walls bad? Do green walls keep people healthy? How do green walls affect chemistry and microbiology of buildings? There's a lot of bio-based materials coming on the market today. This is essentially a sunflower husk cabinetry, and it's actually really taking off in the United States. You see this stuff everywhere, right? So this is a bio-based material. It's very, very attractive. One of my colleagues who is here, Carrie Kinney, has done some research where she exposes these bio-based materials. She doesn't wet them. She exposes them at high relative humidity, 80–85% relative humidity, naturally inoculated, to see what happens to them after 3 or 4 weeks in a high humidity environment. This is what happens to sunflower husk cabinetry. There we go. Turns into chia cabinets. You know, starts growing lots of stuff. So are we basically, in the name of green and trying to be good for the environment, creating and putting materials in buildings that are going to come back and haunt us later on? The third area, and this is really interesting, I think there was 1 paper on engineered nanomaterials at this conference, but engineered nanomaterials are being produced in greater and greater quantities, greater than 10,000 tons per year now around the world, and put in more and more and more products that are used indoors. They're used in photocatalysts, of course, beneficially in sensors, in construction materials, a lot of nanomaterials being used in concrete, gypsum board, wood now as an silver nanoparticles as antibacterial in wood, paint, carpet, furniture, insulation, clothing, cleaners, etc. So what are the health impacts of these things on us? I don't know. There's more and more research on the health impacts of people that work in nano-engineered particle or material production, but we don't know much about lower level exposures. There are some indications that exposures to some engineered nanomaterials can exacerbate asthma, and I give you a reference here. and then oxidative damage to livers and kidneys, and that was stated in the one paper on nanomaterials at this conference. I think this field is wide open, the entire exposure paradigm, from understanding sources of nanomaterials, to transport of nanomaterials, to exposure, to dose, adverse response, and how we eradicate those, mitigate those adverse responses. And the last challenge, before I get to some connections, is to avoid becoming too narrow, and I'm probably overstating this. But buildings have complex and dynamic anatomies. I think that buildings have anatomies that are not that different from the human anatomy. We wouldn't consider the human anatomy to be just one big homogeneous blob with a single organ in the middle of it, right? They're complex systems, and all the complex systems that make up the greater system of the human anatomy talk to one another. If something goes wrong with one part of the anatomy, it can translate to problems in other parts of the anatomy, and the same thing is true of buildings. So we can't just be heart surgeons. We have to understand that the heart, the cardiovascular system, et cetera, has impacts on the other parts of the building. I've not included everything in this plot here, but I just threw out a lot of the things that are important in buildings or that we study and tried to draw lines where I felt that there were strong connections between those things. And you can see when you do that, you develop this pretty complex web, right? People that study thermal comfort, tend to focus on temperature and relative humidity and airflow around the body. But as you adjust those things, how does that affect indoor chemistry and microbiology and emissions from different products, right? It's all tied together. And right in the middle of this web are occupants. We care about that part of the web because that's really what we want to care about in buildings. We want to make better environments for the occupants of buildings. But the occupants also have tentacles that affect all of these things through our activities inside buildings. Until we kind of understand all these connections, I think we're going to be limited in making significant advances to derive healthier buildings, buildings that are more comfortable, more productive, and in which we can learn. So making connections will generate opportunities for us, but we have to start thinking about making those connections and not just focusing on one organ in the building anatomy. All right, making connections. So I'm going to conclude my presentation with 6 or 7 examples of connections. And I'm not saying these are the most important connections as much as just examples to hopefully get you thinking about the kinds of connections that can occur in buildings. And I'll start with the simplest possible environmental thing that we can measure, and that's temperature. And oftentimes we measure temperature in the middle of the occupied space, and we say that characterizes the temperature of the building. Nothing could be further from the truth. If you look at a cross-section of any building, say in the summertime, but this could be wintertime, we'd have slightly different temperatures here, and you look at temperatures in the various spaces of the building, in the occupied space it might be 23 degrees C. In external wall cavities that the sun is hitting, it could be 35, 45 degrees Celsius. In attics in the middle of central Texas where I live, you might have 60 degrees Celsius in the attic in the summertime. Crawl space is cooler. Supply ducts 12, 13 degrees C. So you can see 40 degrees Celsius changes in temperature from one location to another at an instant in time in a building. And of course, these all change over time. They're dynamic as well. And you can see the drivers for that there. So what does that mean? Certainly, temperatures that are 40 degrees Celsius difference can have a big impact on off-gassing from materials. You heat up a material 40 degrees Celsius, you're going to get a lot more stuff coming out of it. It can change chemistry that occurs in the material. Can it change microbiology? And to answer that, I'll show you a plot that I love. This is from Jordan Peccia's group at Yale University that shows a connection between temperature, microbiology, and health. And Jordan and his team studied Aspergillus fumigatus, okay, the stuff that'll grow fungal balls in your lungs, aspergillosis. It's also, a lot of people are pretty allergic to it. And he grew Aspergillus fumigatus at different temperatures, sporulation temperatures from 32 degrees down to 17 degrees. And what's plotted here is the protein content of the spores on the inset and the allergenicity, which is proportional to the protein content of the Aspergillus fumigatus at these temperatures. So you can see as you just drop 15 degrees Celsius from 32 to 17, about a factor of 10 increase in the protein content and the allergenicity of the spores. That's dramatic. And it's also dramatic when you take into account that this temperature range is well within the range of temperatures I just showed on the previous plot. So does that tell us perhaps that if we're growing Aspergillus fumigatus in a supply vent, that it might have a much greater impact on individual occupants of the building than if we're growing the same Aspergillus fumigatus in an attic or an external wall cavity? Perhaps. What this tells us is that environmental conditions matter when it comes to microbiology. Some of the same researchers were involved in a study that was published about a year ago, a great study that was really focused on the outdoor environment and how outdoor carbon dioxide levels might affect the allergenicity of different types of things around the world. And this is a plot that actually shows the carbon dioxide level from sort of early 20th century levels increased up to where we are roughly today, I guess just past 392, around 400 ppm, and then projecting 30, 40, 50, 60, 70 years into the future. And what you can see here is the same thing plotted as I showed on the previous plot. This is the allergenicity of Aspergillus fumigatus spores, and you can see as the carbon dioxide concentration increases, the allergenicity increases to a point which happens to be right about where we are today, at around 400 ppm, and then starts dropping as we get to higher carbon dioxide concentrations. The point of this is not to encourage injecting carbon dioxide into buildings to reduce the allergenicity of mold in buildings. The point of it is to show you that relatively subtle changes in environmental conditions may have significant impacts on microbiology, And I wouldn't use these results empirically in some way in a building. They were grown in a substrate you'd never find in a building. But that aside, changes in carbon dioxide concentrations in environmental conditions may affect microbiology in buildings. We don't talk much about sunlight in our society. That's kind of the realm of architects. But it turns out that direct sunlight can have an impact on indoor physics and chemistry. Maybe microbiology. I haven't seen that yet, but perhaps microbiology as well. This is a plot that shows the temperature of a laminated table surface placed in different locations in 3 or 4 different buildings at the University of Texas. Plot was generated by one of my colleagues, Attila Novoselic, is here. And it shows the indoor temperature, about 23 degrees in all cases, and the surface temperature of this laminated table for windows with different solar heat gain coefficients. So high solar heat gain coefficients means a lot of solar energy gets through. Low solar heat gain coefficient means not a lot gets through. What's important here is that you can see that for windows with solar heat gain coefficients of 0.5 to 0.8, a 10, 11, 12 degrees Celsius rise in the surface temperature when there's direct sunlight coming through windows, hitting that surface, can dramatically increase the temperature, 10, 12 degrees. So what does that mean in terms of emissions of stuff from whatever that material is? And what I show here is just quickly some results from a paper published by Per Clausen in 2012 that showed if you have an increase in the temperature of vinyl flooring, the DEHP emissions, and this is a temperature of 12 degrees Celsius, kind of in the range that I'm showing here on the left-hand side, causes a 10-fold increase in emissions. So direct sunlight could cause, for at least short periods of time, 2, 3, 4 hours during the daytime, a dramatic increase in SVOC emissions from materials that are sort of within the zone of that direct sunlight. Direct sunlight can affect our exposure to semi-volatile organic compounds. Charlie Wester gave a keynote address Wednesday morning, and gave this wonderful summary about what we know about indoor chemistry and all the different chemical reactions that occur indoors. There have been different teams that have been developing models to try to predict the levels of different types of pollutants derived from indoor chemistry over the last 20 years or so. And one of the things we try to predict is the amount of hydroxyl radicals that are formed. If we form hydroxyl radicals, we get this whole second stream of oxidation chemistry going on that can generate some interesting things. It's been assumed to this point that most of the hydroxyl radicals that are formed indoors come from ozone reactions with alkenes, with unsaturated organic compounds. Some may occur as small amounts from photolysis of ozone and hydrogen peroxide. But everything we've done so far has been modeling. And our models predict hydroxyl radical concentrations indoors on the order of 10 to the 4th to 10 to the 5th radicals or molecules per cubic centimeter. HONO, nitrous acid, can also photolyze and form hydroxyl radicals at wavelengths of light less than 400 nanometers. And there was a paper published in 2013 in PNAS where I think these are the first direct measurements of hydroxyl radicals in an indoor environment in a school in France. And Gomez Alvarez found that when direct light was incident through windows in the school, that photolysis of nitrous acid could lead to hydroxyl radical concentrations of upwards or exceedance of 10 to the 6th molecules per cubic centimeters. That's almost a game changer in the way we think about indoor chemistry. That's a factor of 10 higher hydroxyl radical concentration than we ever knew existed before. And it's wonderful that it was derived from measurements and not modeling. These are real values, and we don't have to worry about the uncertainties of our models in using those numbers. So direct sunlight has an effect on indoor chemistry. Another connection is humidity and chemical emissions. We oftentimes focus on relative humidity in terms of thermal comfort or microbiology in buildings, but it turns out that water vapor and air also increases or enhances hydrolysis reactions in materials. Certainly formaldehyde is one that we know about, but other hydrolysis reactions can occur. I've studied a chemical called texanol ester alcohol in paint, and we know that it slowly hydrolyzes over time and forms isobutyric acid, which is sort of the odor of sweat. Changes in relative humidity, changes in relative humidity affect other indoor reactions, and water molecules can displace other molecules that are sorbed to surfaces. We were working in my laboratory several years ago, and we noticed that occasionally we would get these increases in texanol, sort of a natural background texanol in the laboratory, and we couldn't figure out why. We finally noticed that every time the relative humidity went up in the laboratory, we were seeing higher levels of texanol in the laboratory. Our lab hadn't been painted, and the main source of texanol is paint, for over 10 years. But still, as the relative humidity increases, the texanol concentrations increase in the laboratory. So it gave us some ideas, since we were studying texanol, to take some texanol substrate, gypsum board that had been painted with texanol as a substrate. And we took texanol, or painted gypsum board that was over 5 years old, and we put it in a chamber, and we changed the relative humidity in the chamber. And these are the kinds of results. And this is 5-year-old paint on gypsum board. And you can see as we increase the relative humidity, we get this dramatic increase in the emissions of texanol. And as we lower the relative humidity and we go backwards, we see it go right back down to where it was. So changes in relative humidity that are within the realm of the kinds of things we talk about can have an impact on off-gassing. And I asked the question, is this an understudied connection between dampness and health? Everything we hear about dampness is it's got to be some biological agent that's causing the problem. Could it be that as we have zones of really high relative humidity where there's dampness, we could have hydrolysis reactions that are forming who knows what that we're exposed to, and we're also displacing a lot of molecules from materials, and we're exposed to those as well as biological agents. Back to the cumulative exposure issue. So we took this out in the field. We went to 6 different homes, twice in every home, 3 times in one home, and we did forced relative humidity transients in the homes at a constant temperature. All right? And what we found when we did that was, and the blue bars here correspond to the total abundance, this was with GCFID, total abundance per cubic centimeter, before we increased the relative humidity, and the red bars are after we increased relative humidity. Each of these values down here is a different chromatographic bin, so this is low boiling point stuff, this is the heavier, higher boiling point stuff. What we found is that in 12 of the 13 cases, we saw increases in the amount of stuff in the air, organic material in the air, as we increased the relative humidity, and not dramatic increases. We were going 40 to 60, 45 to 65% at 23, 24 degrees C. So realistic relative humidity increases. In some homes, we would see relatively small increases. In some homes, we'd see dramatic increases in the amount of organic material in the air as we increase the relative humidity. On average, our mean total abundance increase was 260%, but there was significant variation between the homes. We did mass spec analysis. We collected samples and tried to characterize what chemicals were in all these bins. We saw a lot of terpenes, fragrances, a lot of fragrance alcohols, terpene alcohols, stable carbonyls. In a few homes, really high concentrations of paradichlorobenzene increases, texanol ester alcohol from paint, and a few other things. Most of these things we think were in products that were previously used in the homes, or perhaps even from some indoor chemistry, and had stuck to indoor surfaces. Some homes had more stuff stuck to surfaces than other homes, and when you increase the relative humidity, you just drive all the sorbed material off those surfaces, and that's the phenomenon we're seeing. All right? But changes in relative humidity don't just affect comfort, and they don't just affect microbiology, they can also affect chemicals we're exposed to in indoor environments. There are connections between chemistry and microbiology, and these really need to be explored. This is one simple experiment, or one set of experiments that were done by a previous PhD student at the University of Texas, and these were experiments that were actually done after she left the University of Texas. and was doing a postdoc at NIST in the United States. And what she did was she exposed bamboo and she exposed red oak, both very common flooring materials in the United States, to different levels of ozone. So she ozonated them. She essentially oxidatively aged them, and then looked at, after natural inoculation, actually artificial inoculation, I believe, how quickly mold grew on the surfaces of these materials. And what she found is, as the materials were oxidatively aged for longer periods of time, the time it took to grow mold on them substantially decreased. Oxidative aging of the materials makes them more susceptible to mold growth. Did FTIR analysis of the surface of these materials. This is one example. And this particular line right now corresponds to carbon-oxygen stretching bands in the FTIR analysis. And you can see that it's increasing over time, suggesting is that as the materials oxidize, we're accumulating organic acids, carboxylic acids, carbonyls on the surface. And for whatever reason, because I'm not a microbiologist, mold seems to like that environment. All right. And the last connection is the connection between ventilation pathways and indoor air quality. We seem to talk a lot about increasing ventilation to solve problems. We talk about that sometimes, or characterize air exchange rate in buildings as a scalar quantity, a single value, right? But it turns out that the pathway that air takes when you're ventilating a building is also very important. I've been involved with a study in Tennessee. One of my PhD students has been working with Oak Ridge National Lab. I've actually never been there. I've only been on the phone and doing web stuff with them, but helped to guide the research. And there's 3 homes in Tennessee which are billed as homes of the future. They're almost hermetically sealed. The air exchange rates in 2 of these homes are on the order of 0.01 air changes per hour. 100 hours for 1 turnover of air, right? They're almost zero energy homes, but the formaldehyde concentrations in these homes are so high that nobody can live in them. So we're saving energy and potentially making people sick, right? So the question is, can we ventilate these homes in a way that we reduce the formaldehyde concentrations, and what would be the cost of doing so? So the results that you see here are formaldehyde reduction in percent for different events that we carried out for supply ventilation, positive ventilation, and exhaust ventilation or negative ventilation. And you can see here with supply ventilation that's positive, when we increase the air exchange rate from 0.02 to about 0.4 air changes per hour, we get about a 55% reduction in formaldehyde in this particular home. In the next one, 0.13 to 0.34, we get about a 40% reduction. In the last one, about a 60% reduction. When we go to exhaust or negative ventilation in these homes, and we increase the air exchange rate by what, about a factor of 16? 0.01 to 0.16 air changes per hour, we actually see an increase in formaldehyde concentration. In these cases, when we increase the air exchange rate pretty dramatically using exhaust ventilation, we see small decreases in formaldehyde concentration. Why is that? The reason for that is that, especially in the summertime, most of the formaldehyde is coming from external wall cavities, very high concentrations in the external wall cavities, and so when we ventilate using exhaust ventilation, we're sucking air through those wall cavities and essentially sweeping our ventilation air right through the source, all right? The amount of ventilation in both cases, the increase was dramatic, but in one case it actually had a negative impact on indoor air quality, or at least not a very positive impact. The amount of ventilation is important, but so is how you ventilate, right? And think about, as the microbiologist in the crowd, if there's stuff growing in external wall cavities and we use negative ventilation, or in a crawl space and we have exhaust ventilation, what is that going to mean? There we go. What is that going to mean in terms of what else is pulled into the building? So when you're doing research on buildings and studying microbiology in buildings, don't just characterize the air exchange rate. Characterize pressure differences between the indoor environment and the outdoor environment. Try to figure out where the air is coming that's coming into the building, especially if it's exhaust ventilated. All right, so some future connections as I sort of wrap up here. And there's so many of these, I'm just going to give you a couple of examples. Urbanization. We continue as a species through the largest mass migration from rural areas to urban areas in our history. All right, it's continuing. It hasn't stopped. Right? And Imagine people that are living in rural areas that are exposed to a lot of cook smoke. Kirk Smith yesterday gave a great presentation on cook stoves and the ills of cook stoves, right? You take people that are exposed to all the pollutants that are emitted from cook stoves and move them into an environment where now they're no longer exposed to what's emitted from cook stoves, perhaps, but are emitted to much larger concentrations of stuff that comes out of the tailpipe of cars and very, very high formaldehyde concentrations in some new construction in places like Beijing. I think there's real opportunities there to try to understand and study the health impacts of taking somebody out of one extreme environment and putting them in another extreme environment. I show a picture here of Lagos, Nigeria. Sometimes we focus on all the growth in Asia. The African continent is going through a massive urbanization process right now. Lagos, Nigeria, 40 years ago had a population of about 700,000. Today it's 21 million. And the infrastructure in Lagos is not meant to have all the cars that it has on the roads. And if you look here, you can see a lot of apartment complexes right next to these busy roads, like you can see in many cities all around the world. In the United States now, 11% of our population lives less than 100 meters from a major four-lane highway. We're creating what are called freeway communities. 50% of our population lives within 200 meters of a major roadway. We're a very urbanized society, and the rest of the world is catching up with us in terms of urbanization. It's not just what comes out of the tailpipe of the car, and this is another sort of connection or link. If you take samples of road dust near any busy road, you're going to find a huge amount of metals. Metals from brake lining, metals from tires, lots of metals from catalytic converters on the roadway. And that dust gets into buildings that are adjacent to those major freeways. So I would ask the question of the microbiologists in the crowd. I don't know the answer, but perhaps do buildings or homes that are located right near busy freeways have a completely different microbiome than homes that are located 500 meters away from the freeways because of all the metals and the dust that comes into those homes? It's a possible connection, maybe an opportunity for future research. All right. So as an engineer, of course, I want to get involved with engineering controls and strategies on buildings that are near roadways, and that's kind of meat and potato stuff, but it's something we need to do more of. I took out some slides on climate change because I knew Jenny Sue was speaking before me, and Jenny Sue talked about extreme events. The other side of climate change is how we adapt to it, how we try to mitigate it, and how we change buildings to try to mitigate climate change. A lot of new materials are being brought into buildings that have low embedded energies. I've already mentioned some green materials. I won't dwell on those. But we do need to understand the chemistry and microbiology of those materials. There were 2 papers presented at this conference by Dustin Poppendieck on envelope emissions from tight buildings, wrapping buildings in different types of wraps, or using spray insulation, polyurethane foam spray insulation. Dustin told me yesterday that about 100,000 buildings a year in the United States, of about 600,000 new homes, about 100,000 of them are being, spray insulations being used with polyurethane foam, which has lots of flame retardants in it. So in his experiments with certain wraps and spray insulation, he sees increases in flame retardants in the indoor environment and increases in other heavy hydrocarbons from the wrap material itself. There's a trend in the United States. Maybe we're going to go full circle. I don't know. I grew up in about a 1,000 square foot house, a 100 square meter house with a family of 4. Now in the United States, a small house is about 300 meters squared, I guess. But in Austin now, there's a big push to build more micro units. And a micro unit is defined as a residence that's somewhere between 30 and 50 meters squared. All right? And the reason for that in big cities is that cities are getting very, very expensive, for one. And so it's hard to purchase big McMansions. But there's a big demand for micro units. And as we move towards smaller residential units, we're going to have greater occupancy density in those units. What is that going to mean for the indoor environment in terms of microbiology and chemistry? How are occupant activities going to change in smaller housing? When we move to smaller housing, we're going to have a much larger surface to volume ratio. That means surface phenomena become much more important. What does that mean in terms of chemistry and microbiology on surfaces in smaller buildings? And then connection, occupants and everything. This is my last connection, and it's so important for us to realize that what we do and how we design, construct, operate, maintain buildings is for the occupants of the buildings, for human occupants, but perhaps for pets and livestock and that type of thing if you're interested in that part of our field. But also that we have probably more impact on our indoor environment than any of the other things up here. We set thermostats. We buy products and bring them into the indoor environment. We vacuum. We allow our pets in or out of the house. We do all those things, and we're the ones that have the greatest impact. And it strikes me, how many people here, if there's one toxicologist, how many people got their degrees in social science? 0. So in the room right now, in our community, there isn't a social scientist in the room. I think that's really sad. I think it's really sad because occupants and what we do in buildings has a greater impact, as I said, than anything else in the building. And I wonder whether as a community in the future, to make connections between occupants and all the other things in the building, we need to embrace the social sciences, and especially the field of psychology, right? What we feel is perceptions, and perceptions impact what we do. And we do have some people in our society who study perceived air quality, but not other types of perceptions. What we do, our activity patterns, are based upon, in part, who we are and what our personality traits are. Right? I've been involved with a study with a psychology professor at the University of Texas, and we've been using the most sophisticated personality trait typing that you can in the psychology field, and then asking people about aspects of indoor air quality or what they do in their everyday life. Do they burn candles? Do they avoid this? What are they sensitive to? How often do they vacuum? How often do they change the sheets in their bed? That type of thing. And what we find are some interesting results. In terms of 10 different sensitivities we described, people that have a high level of neuroticism, and I hate to admit I've taken the exam, I'm kind of on the high side of neuroticism, but people that have a high level of neuroticism tend to respond that they're much more sensitive to 9 of the 10 things. They have statistically significant, highest sensitivity, highest association of all the other 4 personality traits. Things like pollen and cats and dogs and musty odors and all those things. The one sensitivity the one thing they're not sensitive to that people with other high levels of personality traits have, for whatever reason, is environmental tobacco smoke. Don't know why. And this includes a lot of people that are neurotic and don't smoke. So I think those kinds of things are interesting. I don't know how we use them, but we can be creative and try to make connections if we're willing to work with the psychology community. Why do we feel X or do Y, and what makes us change? And this is one example of something that I think is very fascinating. Odors mean a lot of different things to different people. This is actually a product in the United States that I've been talking about for a few years now, and I've never actually seen it in practice until recently when one of my staff members in my department had her office painted, and she insisted that this product be used in the paint. And what you have here are little packets that you open up, and you stir them into the paint, and these are basically scenting agents that make your paint smell good. So when you paint the walls in your office or your room, they continue to smell and smell good. When I walk by Alicia's office, I get this big gush of what smells like Hawaiian tropical breeze every time I walk by her office. It's been 3 months now, and you can still smell it. But in this advertisement here, you can see the words sense easily and immediately evoke memories and feelings. Right? That changes what people do in buildings. It may change how much time they spend in a building, or how little time they spend in a building, or the activities they're engaged in a building. And this particular product states that the product continues to scent the environment for up to 5 years. It's been 3 months in Alicia's office, and I can still smell tropical breeze when I walk by her office. Right? What's in these containers is incredibly unsaturated, incredibly reactive with ozone. Right? And so by using these products, individuals are actually making their environment a much more chemically reactive environment. Here's a link between psychology and chemistry. All right? Got to make those connections. I find it interesting that one of these products here has the name Clean and Crisp, and it actually says refreshing like an open window on a spring day. So we've gotten to the point in our society but we have to paint our walls with stuff that smell so that the indoor environment could actually smells like what it would smell like if we just opened a window. It's sort of interesting. So onward to an exciting future. I think as we move to the future, and I'm speaking to young people now, I don't understand some of these things that are up here. There are a lot of new tools that are going to, I think, revolutionize what we do. New tools including wireless sensors that can detect with much greater sensitivity pollutants in the indoor environment as well as biomarkers, health biomarkers. Big data. There are so many databases now, and I think that Jenny alluded to this, that we can pull information from and use to better understand population exposures to pollutants in indoor environments, et cetera. There's also an ability with wireless sensors to generate huge amounts of data very quickly in buildings and to synthesize that and use it for the benefit of occupants of the building. And then advanced instrumentation that has been used by other fields that's being brought indoors, high-throughput DNA sequencing. And the Sloan Foundation was very visible at this conference, and there's just so much exciting research going on sort of non-culture-based analysis of microbes in buildings. PTR mass spectrometry, aerosol mass spectrometry, laser-induced fluorescence phage. We heard some, I think, from Charlie Weschler on Wednesday about advances in that area. So things that are being brought indoors now that we've never brought indoors before that hopefully we'll learn a lot about. So my advice for young people that are here today are to become grounded in scientific principles. If you're not grounded in scientific principles, you won't be able to make connections. Use technologies not simply because they exist, but to make connections. Think about how you're going to use these technologies to help make connections to derive better buildings. Be willing to reach across disciplinary boundaries. That's the only way you're going to make connections that improve the quality of buildings. And did I say make connections? So make connections. And I'll leave you with a quote from Charles Darwin. And that is, it's not the strongest of the species that survives, nor the most intelligent that survives. It's the one that is most adaptable to change. And one more time, for us that sort of narrow focusly on what we do, be willing to sort of spread out, talk to others that do other things, make connections, because it's those connections that are going to allow us to overcome challenges and make buildings better environments for us. All right? So I'll leave you with that. Thank you.
Thank you very much, Rich, for your very thought-provoking presentation and reminding us not to forget that we need to make the connections between each other and especially back to the human in the indoor environment.